How do powered wheels propel a bicycle or car forward? The answer to that question is that the ground exerts a forward static frictional force on each powered wheel and thereby pushes the entire bicycle or car forward. In the previous video, however, I pointed out that the ground exerts static frictional forces on free wheels as well. So what could be different between free wheels and powered wheels? To explain that, let me start by re-examining free wheels. When you pull a wagon forward so that it accelerates forward, the bottoms of its wheels are threatening to slide forward relative to the ground. And so static friction acts to prevent that sliding. It pushes the bottoms of the wheels backward. And that backwards force of static friction on the bottoms of the wheels has two effects. First, it produces torques on the wheels that cause those wheels to begin to spin, to roll. And so when I pull the wagon forward and its wheels rolls, that's because of static friction with the ground. But second, those backward frictional forces on the bottoms of the wheels affect the entire wagon. And you have to pull a little extra hard and do a little extra work to get the wagon up to speed because its spinning wheels are carrying extra kinetic energy, something we'll explain in the next video. The key point here is that the ground pushes free wheels backward as their vehicle accelerates forward. In contrast, the ground pushes powered wheels forward as their vehicle accelerates forward. To explain that observation, I need a powered wheel. Wagons don't normally have powered wheels, so I have to add one. And here it is. It's a cordless electric drill with a big rubber stopper. And when I turn on the drill, it twists the rubber stopper and the stopper begins to spin. Well, in the language of physics, the drill exerts a torque on the rubber stopper and causes the rubber stopper to undergo angular acceleration. If I press this stopper against the sidewalk, the stopper becomes a powered wheel, and it propels the vehicle attached to it forward. At present, the vehicle it's going to power and propel is me. And when I turn on the drill, it pulls me forward. Now, where does this come from? It comes from the fact that if I were to spin the wheel above the sidewalk here, the bottom of the wheel will move in the backward direction relative to the sidewalk. And once I touch the two surfaces together and static friction appears, it's going to fight that relative motion. It does not want the bottom of the wheel moving backward. And therefore, it will push the bottom of that wheel forward to oppose sliding and to try to keep those two surfaces at the same velocity. That forward force on the bottom of the powered wheel has two effects. Does that sound familiar? One effect of that forward static frictional force on the bottom of the wheel is to produce a second torque on the wheel that opposes the drill's torque. It acts to slow the angular acceleration of that wheel. It's fighting the drill. That's one effect of that forward frictional force on the bottom of the wheel. The second effect is it's a forward force on the entire vehicle. It causes the entire vehicle to accelerate forward, namely me. Whoa, off we go. So, a powered wheel obtains a forward static frictional force from the sidewalk that propels the vehicle forward. Well, I don't make a very good vehicle. So, what can we do better? Well, I have a big wagon. I have a powered wheel. Let's go on a road trip. Here we go. Powered wheels on a wagon. Full speed ahead! Yay! That worked out pretty well, and I'm still in one piece. It's time for a question related to powered wheels. At a track and field competition, the runners in a 100-meter sprint start that race with their feet pressed against the nearly vertical surfaces of starting blocks. Their feet against those blocks, and they're wearing spikes that project into the track as they run. Why are the starting blocks and spikes important to the runners in a 100-meter sprint? To win a sprint like this, the runner wants to accelerate forward as rapidly as possible and may well be accelerating even as the runner crosses the finish line. At the start of the race, the runner has to be motionless before the gun goes off. So the runner has feet pressed against these nearly vertical surfaces of the starting blocks. When the gun goes off, the runner pushes back hard on the starting blocks with support forces. These two surfaces are attempting to occupy the same space at the same time. So as the runner's foot pushes back on the starting blocks hard, the starting blocks respond by pushing forward on the runner's feet hard. And that helps the runner get started from the moment the gun goes off. Once the runner loses contact with the starting blocks, however, all they have to push against is the horizontal track surface. So to get a forward force out of a horizontal surface, you need friction, and ideally static friction. So having spikes on your shoes as a runner allows you to get better traction, that is a higher maximum static frictional force out of the track. So with those spikes digging into the track, you can get forward forces that are enormous on a human scale and accelerate forward at a dramatic rate. And so the best sprinters obtain very large support forces out of the starting blocks and then maintain their acceleration by getting very large forward frictional forces of static friction toward the finish line. And they may well still be picking up speed in the forward direction as they cross the finish line. I've talked a lot about powered wheels, but I've never actually defined the term power. People often use the words power and energy interchangeably, but they're actually different, though related, physical quantities. Energy is the conserved quantity of doing, and power is the rate at which energy, that conserved quantity, is transferred from one object to another. In more official language, energy is the capacity to do work, and power is the rate at which that work is being done. To shed more light on this relationship between energy and power, let's revisit the energy-money analogy. Just as energy is the conserved quantity of doing, money is the conserved quantity of spending. If you have energy, you can do work. If you have money, you can spend. Spending transfers money, just as doing work transfers energy. When you buy something, you spend a specific amount of money. Similarly, when you complete some mechanical task, you do a specific amount of work. Money and spending are measured in your local currency, which might be dollars, it might be euros, or something else. Energy and work are measured in the SI unit of energy, the joule. But there are other units. What about when you rent something? You're not buying it outright all at once. You're paying for it steadily over time. Rather than a one-time transfer of money, there's a sustained flow of money. A dollar, a dollar, a dollar. And like rent, salaries, wages, subscriptions are also these sustained flows of money. And you usually measure them in your local currency divided by a unit of time. For example, dollars per hour, or euros per year, or bahts per day, or rupees per month. Analogously, when you're pedaling your bicycle, you're providing a sustained flow of energy to the bicycle's powered wheel. The rate at which energy is flowing, that is, the work you do per unit of time, is the power you're providing. A typical bicyclist transfers an energy of 100 joules to the powered wheel in a time of 1 second, corresponding to a power of 100 joules per second. the SI unit of power is the joule per second, which is so important that it has its own name. It's called the watt. A typical bicyclist provides a power of 100 watts to the bicycle's powered wheel, or 100 joules per second. There are other units of power, but they're all related to watts. For example, 1 horsepower is equal to about 750 watts. A serious bicyclist can provide about 750 watts, or 1 horsepower, to the powered wheel of a bicycle, at least for a short period of time. To help you distinguish between energy and power and joules and watts, let me ask you a question. If your toaster is labeled as using 1,000 watts, how much energy does that toaster consume in 1 hour? A toaster that consumes power steadily at a rate of 1,000 watts, that is 1,000 joules per second, will consume 1,000 watts in 1 second, 2,000 watts in 2 seconds, 3,000 watts in 3 seconds, and in an hour, which corresponds to 3,600 seconds, that toaster will consume 3.6 million joules of energy coming in the form of electricity. So 3.6 million joules is kind of an awkward number to talk about. So it has another name. It's called a kilowatt hour. So when you see written on a power bill, electric power bill, for example, that you have consumed energy in total of 1 kilowatt hour, that's 3.6 million joules of energy. The energy that would be consumed by a 1,000 watt device like a toaster in the course of a single hour. Powered wheels are rotating objects, and the work that's done on them is done in the context of rotation. That's an interesting complication. Rotary work. We've seen that you can do work on a translating object by pushing it and having it move in the direction of your push. You exert a force on it, and it moves a distance in the direction of that force. But what about a rotating object? It turns out that you do work on a rotating object by twisting it and having it turn in the direction of your twist. You exert a torque on it, that's a twist, and it rotates through an angle in the direction of that torque. For example, when I spin this bicycle wheel, I do work on it. I exert a torque on it, I'm going to twist it, and it rotates through an angle in the direction of my torque. My torque was toward you, and it rotated toward you. So I'm transferring energy to it, and you can see that energy because it's moving. It's got kinetic energy. Getting the units right when doing work in a rotational context is a bit tricky. You have to be careful to choose the correct units when measuring angles. Those angles should be measured in radians, the natural unit of angle. And as a reminder, 1 full rotation like this is 2 pi radians, where pi is the mathematical constant that's approximately equal to 3.14159. So 2 pi radians is about 6 1/4. That means that if I rotate this wheel all the way around, that was about 6 1/4 radians. Well, if you choose that unit to measure your angles in, and you use the SI unit for the torques you exert, you end up with the SI units of energy when you figure out how much work you've done. So, for example, if I exert a torque of one SI unit, which is 1 Newton meter, that's the unit of torque on this wheel, as it rotates through an angle of 1 radian in the direction of my torque. I'm going to rotate it like that towards you, and it's going to turn toward you. So I'm going to follow all the rules. So here you go. I'm going to exert a torque of about 1 Newton meter, and I'm going to do it as the wheel rotates through 1 radian. So I've got to go from about here to about there. That's about a radian. Here we go. Ready? Get set? Okay. I did about 1 Newton meter times 1 radian. 1 joule of work on the wheel. So I transferred about 1 joule of energy to the wheel, and that was the goal here. For a powered wheel, like my drill-powered rubber stopper here, the rotary work is done at a steady rate, so the drill is providing rotary power to the wheel. Before I show you how to calculate power in a rotating system, let me show you how to calculate power in a translating system, this wagon. If I push the wagon and it moves steadily in the direction of my push, I'm providing it with power. And the amount of power I'm providing it with is the work I do on it per second. In this case, that is the force I exert on the wagon times the distance it travels in the direction of that force per second. Well, the distance it travels in the direction of my force per second is its velocity, at least the part of the velocity that is in the direction of my force. So, the amount of power I'm providing in this translating object, the wagon, is simply the force I exert on it times its velocity, where we're only considering the part of the velocity that's in the direction of my force. That's the power in a translating object. Now we can return to the power in a rotating object. That rotary power is the rotary work the drill does on the wheel per second, which is the torque that the rotary drill exerts on the wheel times the angle through which the wheel rotates per second. That angle through which it rotates per second, that part, is just the wheel's angular velocity. So in short, the rotary power the drill provides to its wheel is the torque it exerts on the wheel times the wheel's angular velocity, the angle through which it rotates each second with all the directions done properly. If some of these details about rotary work are too complicated to follow, don't worry about them. The takeaway message is that if you twist something and it turns in the direction of your twist, you're doing work on it and transferring energy to it. And if you twist it and it keeps moving, you twist and it steadies, then you're providing it with rotary power. When you do rotary work on a wheel, you give it energy. We'll look at what becomes that energy in the next video.